Welcome to today's episode, where we're diving into the intriguing realm of distributed systems. As our digital world becomes more interconnected, it's essential to grasp how these systems can agree on values and maintain reliability. We'll explore the complexities of consensus algorithms, the challenges that arise in asynchronous environments, and the vital role of the Zookeeper Atomic Broadcast, or ZAB protocol, in achieving consistency across distributed networks. Now let's talk about the heart of distributed systems, the challenge of achieving consensus among multiple processes. Consensus algorithms are crafted to help these processes agree on a specific value, but it's not as simple as it sounds. One significant hurdle is the FLP impossibility theorem, which points out that in a completely asynchronous environment, it's impossible to guarantee consensus within a set time frame. This theorem really highlights the difficulties that come with ensuring all processes can reach an agreement, especially when they encounter failures or delays. To navigate these tricky waters, we need to consider the trade-offs involved in consensus algorithms. There are a few key properties that any effective consensus mechanism must uphold. First, there's agreement, meaning all correct processes need to agree on the same decision value. Then we have validity, which ensures that the proposed value is one that was suggested by some process. Finally, we have eventual decision, which guarantees that all correct processes will eventually decide on a value. These properties work together to help systems function reliably, even amidst the complexities of distributed environments. Effective communication among processes is another essential piece of the puzzle, particularly when it comes to broadcasting information. Reliable message delivery can be quite challenging, especially if a coordinator crashes, which could lead to inconsistencies in the system. This is where reliable broadcasting comes into play, ensuring that all correct processes receive the same messages. Atomic broadcasts take this a step further by guaranteeing that messages are delivered in a consistent order, which is crucial for maintaining the integrity of the information being shared across the system. So, how do we enhance the reliability of message delivery even more? Enter virtual synchrony. This concept groups processes together, making communication and message dissemination more effective. By ensuring that messages are delivered atomically and in the right order, virtual synchrony helps to alleviate some of the challenges associated with distributed consensus. Now, let's focus on one of the most widely used implementations of these ideas, the Zookeeper Atomic Broadcast, or ZAB protocol. ZAB is specifically designed to maintain consistency across distributed systems by appointing a leader who manages message broadcasts and synchronizes followers. The way this protocol is structured ensures that all processes stay aligned, even when failures occur. The ZAB algorithm unfolds through several key phases, each of which is crucial for maintaining consistency in distributed systems. It all starts with the synchronization phase, where a new leader proposes itself to the followers. During this phase, the leader collects acknowledgments from the followers to ensure they're all in sync with the established history. This initial step is vital for aligning all processes before any further actions can be taken. Once synchronization is achieved, we move into the broadcast phase. Here, the leader receives messages from clients, establishes their order, and sends proposals to the followers for acknowledgement. This phase mimics a two-phase commit process, accepting only valid proposals from the current epoch. This mechanism ensures that all processes are working with the same set of information, which is crucial for effective consensus. Lastly, we have the safety mechanism, which is essential for the integrity of the ZAB protocol. It ensures that followers only acknowledge proposals from the rightful epoch leader, preventing conflicts and guaranteeing that there's always a single leader guiding the consensus process. As we wrap up this episode, we hope you've gained a deeper understanding of distributed consensus and the mechanisms that support it. The challenges of achieving agreement among processes in asynchronous environments are significant, but protocols like ZAB help ensure consistency and reliability in distributed systems. The interplay between consensus algorithms, reliable broadcasting, and the structured phases of the ZAB protocol reveals the intricacies of maintaining order in our interconnected digital world. Join us next time as we continue to explore more topics in distributed systems and their implications for technology today. Thank you for listening.